Welcome to the final plenary of ISIT 2015. It's a pleasure to introduce Ruediger Urbanke. I was fortunate to have Rudy as a colleague and consider him a very dear friend. And in the IT society, Rudy requires almost no introduction. He has been in the forefront of almost all major developments in modern coding theory, and starting from his work with Richardson on analysis of LDPC codes and demonstrating that it's close to Shannon capacity, and development of density evolution, for which has been used for almost all developments in LDPC code since. He has made major contributions to polar codes and also to spatially coupled codes where he's demonstrated it's close to capacity. For this and other works, he has won many awards, including the IEEE Koji Kobayashi Award, the IEEE Hamming Medal, and he has won the IT Society Paper Award twice, a distinction that is shared among three other people, all of whom are Shannon Award winners. He has been an incredibly positive influence in the IT society, which he has not only been through his works, also through his mentorship of students. You can see the number of his students who have actually won awards. And it's almost easier for me to list, instead of listing all his accomplishments, I thought I can have a roll of paper to do this, but I decided not to do that. And he has also has an incredible amount of service to the IT Society, including being the Vice President of the IT Society currently. And Ruediger has an incredibly positive personality, and he's generous to a fault, even when he makes fun. And since this is the last plenary, I thought that before giving the floor to Ruediger, we will ask some technical questions earlier. So Ruediger. So Ruediger, so what's your favorite animal?
Okay, animal, I would say probably dogs, because we always had dogs in the family, and one reason I have a particular affinity is because when I was young, my parents wanted me to really play piano. And I really didn't like to play piano. I did everything to, get out of it. And the only way that finally I did get out of it is because our dogs simply couldn't stand it when I was playing piano. And since dogs have very high priority in our family, finally I was let off the hook.
So have you ever run out of gas in Lincoln Tunnel in a red Golf?
No.
Are you sure?
No.
Absolutely sure? I heard something about this.
No. I got stuck once in the Holland Tunnel, but not in the Lincoln Tunnel.
So say that someone asked you about something old, something new, something borrowed, and something proved. What would you say?
It's funny you would ask. Just by sheer coincidence, I prepared a few slides, and so if you don't mind, maybe I'll tell you about them. So it's... So it's a great pleasure to be here. Thanks a lot for the organizer, of course, a great honor. This is a joint work with Superman here, also known as Srinivas Kudekar, who was a PhD student at EPFL and is now at Qualcomm. This is Marco Mondelli, since Marco is mostly working on polar codes and he has a very crazy hairstyle. We typically call him Marco Polar. And that is Aaron Sasoglu, who was also a PhD student at EPFL and then was a postdoc both at UCSD and Berkeley. Now, it turns out, whatever I'm going to tell you about it is we were not the only ones to have the idea. There was a second group, and these people are also in the audience. This is Santosh Kumar, and this is his advisor, Henry Pfister. And not only did they think or work on exactly the same problem, it turns out they had exactly the same idea and exactly the same solution. So it just happens that I'm now here on stage to tell you about this story. It just happens that it's me, but it could be any of these 6 people that were up there. They would tell you exactly the same story. The only difference is that, the accent would be slightly different, okay? Right now, it's Austrian, but, maybe if you prefer, you could have had some different accent. Now, what is it that I tell you about? It's Reed-Muller codes, and it's something that we actually heard a fantastic talk already by Madhu on Wednesday. I'll have a slightly different angle on it. And Reed-Muller codes in 1954. This is Muller, I guess that's at least what Muller. Muller, okay. So this is Muller who invented them, and really shortly just after that, Reed came up with a decoding algorithm. And if you look at any classical textbook, there's a lot of information. They have beautiful properties. Typically, in classical textbooks, you find whole chapters dedicated to the various algebraic properties of Reed-Muller codes. Now, after, perhaps in the 70s, 80s, there wasn't really that much work, and there were really then, in the last maybe 20 years, a few people that consistently, thought about Reed-Muller codes. Just as one example, this is Ilya Duma, who has, worked quite a lot on these kind of codes, and has, has quite a few nice results about them. Now, about the last, perhaps 10, 15 years, and then there's of course also the thread that comes in the computer science literature. But if we're thinking of our community, in the last, maybe 10 years, Reed-Muller codes have picked up, and one of the reasons is their close connections to polar codes. So if this is the matrix, the Hadamard matrix here that describes, the polar codes, but also Reed-Muller codes, so then both of them are described in here. The only difference is, so these are the input bits, these are the output bits. The only difference is of which of these rows, so this represents the generator matrix, which of these rows you actually pick. And so in the polar code jargon, you would freeze some, the ones you don't pick, and you would use some other ones, right? And so the way this would work is whenever you put in here 1, let's say, and all the rest is 0, that's just a matrix here, then you would get a certain number of ones out here. So this corresponds to the generator corresponding if you switch on this bit. And for Reed-Muller codes, what you would do is the ones you pick, the good ones, would simply be the ones that have large minimum distance. So you pick whatever rate you want, you pick the ones that have the largest minimum distance. And so that's how you would pick the generator matrix for the Reed-Muller code. Versus for polar code, you simply follow the order, the successive decoding order given by Erdal. So this is, you first decode this, then this, etc. And assuming that you have decoded everything right in the past and that the future is unknown, there's a reliability associated to this synthetic channel, and you would pick the ones that have the best reliability. Okay, so it's known how much they share. It's known that in general, if you have a code of rate R, that the fraction of generators that they share is again R, okay? So R squared of them are common, and some of them are not. So for very high rates, they're fairly close. For very low rates, they're fairly different, the codes. But they all come from the same matrix here. Good, now, even though, a lot of it is known, maybe it's first another motivation, why is it that we now, since we already know that polar codes achieve capacity, why are people still, going back now to Reed-Muller codes? And another motivation is not just the similarity, but that in a real sense, Reed-Muller codes are expected to be even better than polar codes. So these are some simulations that Marco did, and there's quite a lot of other work of people that did similar stuff. So what is this? This is just a binary ratio channel, length 1000, rate 1/2, probability of error, map decoding. And so this is what the polar code can do. And when I talk here polar code, it's the plain vanilla, no list decoding, nothing. Okay, just the plain vanilla code. And so there's a parameter alpha, and the alpha, when you take it from 1, it's a polar code. If it's 0, it's a Reed-Muller code. It's some kind of interpolation. The exact nature of this interpolation is immaterial to what I say. And if you go closer to Reed-Muller code, you can see that these curves move to the right, so the codes become better. And in particular, you see that for alpha 0, that's the Reed-Muller. And if you plot on top of this just what the random code would do, okay, you can see that they're very close. Okay, so I'm not claiming that's exactly like a random or anything like this, but it's fairly close. And, if maybe you've seen some talks about the scaling behavior of polar codes and so on, it's quite possible that Reed-Muller codes actually have a better scaling behavior. So in that sense, strictly speaking, would be even better. And since they also have a lot of structure, perhaps there's still also a way to decode them. And so, of course, this might then be interesting as a code. Now, no matter how much is known, and classic, a lot of stuff is known, as I told you, there's one even, the most basic question before we can talk about scaling, etc., is that, we don't, the first question is, do they even achieve capacity? Are they good if I'm looking at large block lengths? Okay, that's like the zeros or the bit. These days, that's no longer anything, amazing to talk about, but it's at least a necessary condition that we might be interested in. And so what do we know about it? Well, first let me mention that all of us, the last a few months ago, there was a beautiful program in the Simon Center, and all the people that I mentioned before and actually spent some time there. And I think it was Emmanuel Abe who wrote on the Open POM board actually exactly this question: do Reed-Muller codes achieve capacity? And so I guess that also got several people motivated. And mentioning Emmanuel, the only result so far that we have is exactly some work of him together with Amir Spilka and Avi Wittgersen. And so they give, in a very nice paper, they give some answer to this. And the answer is that if I'm looking at the BC, if I'm looking at rates that go to 0 or 1 at some power of n, so it's 1 over n to a power, think of it maybe as 0.9 or something like that. So you're looking at rates that go either to 0 or 1. Then for the BC, indeed, you can achieve a capacity. And they also have results for the BSC if the rate goes to 0, and if the rate goes to 1, they don't quite show they achieve capacity, but the codes are also not too bad. Okay, so that's essentially what they're talking about. And so what I want to do in this talk, I want to tell you that indeed it's true that they achieve capacity. Now I'm just going to talk about the binary ratio channel and comment a little bit about general channels, but now it's for all rates between 0 and 1. Now, how does this work? Okay. Well, it will turn out that there are exactly 3 things only that we need to know. We don't need to know anything about details of the code. Okay. So it doesn't really.
As I said, there are just 3 things that we need to know to understand how this proof works. In particular, we must understand that Reed-Muller codes are 2-transitive, that symmetric monotone sets have sharp thresholds, and that exit functions satisfy the area theorem. And with these 3 ingredients, we can see how Reed-Muller codes achieve capacity. So, the fact that the automorphism group of Reed-Muller codes is 2-transitive was established by Kasami, Lin, and Peterson in the late 1960s. And in fact, they established many other properties of Reed-Muller codes and generalized Reed-Muller codes. For those of you who are not familiar with what we mean to be 1-transitive or 2-transitive, we want to understand this by understanding for a code, or really for any subset of vectors, what it means to be 1-transitive. As an illustration, we show here 2 copies of the same Reed-Muller code. This is the length 8 Reed-Muller code of rate 1/2. And a code is 1-transitive if for any 2 distinct columns, there is a column permutation that maps the first column to the second column and also leaves the code invariant. So in this case, we have a column permutation that's mapping the first column to the second column. Of course, many other columns are mapped at the same time. And now to see that it's 1-transitive, we're going to look on the other side, and we're going to reorder the rows of that same matrix. And what we're left with is exactly the same vector. So this shows us that at least this Reed-Muller code is 1-transitive. All right, what about 2-transitive? So similarly, we want to map now 2 columns to 2 columns and see that the same thing happens. So in particular, if for any 2 ordered pairs of distinct columns, there's a column permutation that maps the first pair to the second pair, and it leaves the code invariant. And to see this again, we'll reorder our other vector, or our other matrix. And this implies that there's a row permutation that affects the same result, and thus we see that this Reed-Muller code is also 2-transitive. The second ingredient we need for this proof is that symmetric monotone sets have sharp thresholds, and of course this may not sound like it means something to you yet, but in the next few slides we'll see precisely what this means. This result was established in a breakthrough paper by Friedgut and Kalai, where they showed that every monotone graph property has a sharp threshold. For those of you familiar with the theory of monotone graph properties, this was a breakthrough result. And so to understand this, we must first define what we mean by a monotone set. So we're going to let omega be a subset of vectors of length n, binary vectors. And a set of binary vectors is monotone if its indicator function is an increasing function. So the indicator function of the set omega only goes up as we change zeros to 1 of lowercase omega. And so another way of seeing this is that by adding more 1s to any vector, it remains in the set. As an example, we can look at these 3 binary vectors. And what we see is that the first vector, 1, 1, 0, if we change that 0 to a 1, we find that 1, 1, 1 is still in the set. Likewise, if we take the second vector, 0, 1, 1, and we change that 0 to a 1, we find that 1, 1, 1 is still in the set. But if we remove 1, 1 from this set, clearly this is no longer monotone, because there are some vectors which are larger than these, but not in the set. Now, what makes a set symmetric? So in particular, we again have our capital Omega subset of vectors of length n, and this set is symmetric if the set is one transitive. So when I defined one transitive before, I focused on a code, but really this works for any subset of vectors. And so we see that if we look at this set, we have here 1, 1, 0, 0, 1, 1, 1, 0, 1, and 1, 1, 1. We see this set is preserved by cyclic shift. And so this is not all symmetric sets are preserved by cyclic shift, but if the set is preserved by cyclic shift, then it is symmetric. And we see here, if we shift 1, 1, 1 to the right by 1, we get 0, 1, 1, and so on. But if we remove 1, 0, 1, the set is not symmetric, because what happens is we can't interchange the first 2 columns and leave the set invariant. So it's easy to figure out. There'll only be 3 pairs, and there's not enough. All right, the next ingredient we have to think about is the probability of a set. So in particular, we're going to let mu epsilon be the Bernoulli product measure with parameter epsilon. And we want to talk about the probability that an IID Bernoulli epsilon vector is in our set. So we're going to let mu epsilon, capital Omega, be that probability. The reason we care about this probability is later we're going to see that omega is precisely the set of bad erasure patterns. These are going to be the erasure patterns that cause a particular bit to be erased by the map decoder. And now we get to sharp thresholds. So pictured here are Kallai, Friedgut, and Bourgain, who are the key developers of the theory of sharp thresholds, and now we'll also see what we mean by a sharp threshold. So Friedgut and Kallai in 1996 had this paper which says every monotone graph property has a sharp threshold. And what exactly did they show? They said if you take a set which is monotone and symmetric, and you look at this function mu epsilon of omega, that for any delta greater than 0, this function transitions very rapidly from a small value to a large value at some point. And in particular, it's over a window of size 1 on log n. So that the width of the transition vanishes as n increases. And in particular, what we need to see about this is that this threshold becomes arbitrarily sharp as n increases. Now, one thing I should note is it's not very easy to localize this threshold. Many open problems, for example, the threshold of KSAT, is included in, can you localize this threshold? Can you tell me where it will transition from 0 to 1? And in general, this is a very hard problem. So the use of sharp thresholds in coding theory was pioneered by Zemmour and Tillich. And they showed that for the probability of block error, you could use this theory of sharp thresholds to show that every code with a sufficiently large minimum distance actually has a fairly sharp threshold. In particular, they showed if you take a linear code, the BEC, the BSC, even some Gaussian channels, that the threshold width for block map error is going to be order 1 on square root the Hamming distance. And so this is the key idea that we had to put together to see this. So you had to somehow see that exit functions would be important, and you had to know that it might have a sharp threshold. And so, but you still don't know where the threshold is. And in fact, for block error rate, there's no good way to localize the threshold per se. There's not a natural way to localize it. But exit charts were introduced by Ten Brink to understand the iterative decoding of turbo codes, and they've proven extremely useful in the analysis of coding, both for map decoding and for iterative decoding. And in particular, let's first define what we mean by an exit function. I'm sure many of you are aware. but let's make sure we can give some idea what it means. We're going to take a vector, x, and we're going to choose the last bit of this vector to force the parity to be even. So this is going to be a modulo 2 sum, and we're going to take the x vector to be Bernoulli 1/2. So this is a random code word from the single parity check code. And we're going to let y be the observation of this vector through an erasure channel. So a BEC with erasure probability epsilon. In this case, the map decoder can decode any bit in this code if and only if all the other bits are not erased. So if all the other bits, except for say bit I, are not erased, we can just sum them up and compute that value. But if there is one other bit erased, we cannot, and we have to return an erasure. And therefore, the probability of the erasure for the map decoder is given by this simple formula. For the BEC, the exit function is equal to the probability of bit erasure for that bit under extrinsic decoding. And now, extrinsic decoding is when I try and decode bit I, given observations of only the other bits, and not being able to see bit I. So for this code, actually, the exit function is the same for every bit, and the area theorem tells us, this is our exit function, that if we integrate this, we're going to get exactly the code rate. And so, in this case, since we have a closed form solution for the exit function, we can verify this algebraically and see we get exactly that the area under this curve is equal to the rate. More generally, Ten Brink also observed that the area under the exit curve is related to the code rate, and together with Gerhard Kramer and Alexia Schickman, they made this precise and proved that this is true for any code. So for any code on the erasure channel, the area under the exit function is always equal to the code rate. These results were extended to general channels by Meillasson, Montetari, Richardson, and Urbanke through the definition of generalized exit functions. And now we will give a brief summary of the proof of the exit area theorem. And so in particular, we will see it scrolling by in the background so that you can verify it yourself. And the easiest way to see it is...
So the easiest way to see this is by noting that really this quantity that we talked about just now, this probability of the exit decoder to decode correctly, that this is really just the total derivative of the entropy. This is the vector x, the code word, and the observation is with respect to the underlying parameter of the binary erasure channel. And so if you take this total derivative here and you write it as sum of partial derivatives as this thing showed up here, which we're not going to go through in detail, you will see that each of them simply corresponds to a partial derivative, and hence, if we integrated that back out, the area theorem is true just by definition. Okay, so there's not really anything to be proved. It's by definition the derivative, and hence if we integrate it out, it will be, again, the entropy. And of course, if we're integrating the entropy out between something that's not known at all and something where we know everything, then what we just get the entropy of the vector x, and that's just the rate of the code. Okay, so there's really nothing magic that we have in here. Good, so let's summarize, right? So we had 3 ingredients that we needed. We saw that the code is highly symmetric, and we talked in particular about this 2-transitivity, okay? Then we talked about that symmetric and monotone functions have sharp thresholds. This was the Kalife, Reed-Good, etc., and many other people involved result. And finally, we talked about that exit functions satisfy the area theorem. So let's try now to put all these things together. Now, how does the proof go? Okay, so where is the proof? So clearly, the aim will be to somehow define one of these sets and then prove that it's monotone and symmetric. So what is this set? The set will be associated exactly to this exit decoder. So rather than having a block decoder, it's similar to a bit decoder, but with a slight difference. So we're going to try to determine the ith bit, but we are not actually given the whole vector y. We are not given the observation directly. Okay, that's what makes it an exit decoder. So I give you everything except the observation directly, and I'm asking you, can you determine the ith bit based on simply the code constraints from the rest? And so now if you think a little bit about it, you will see that for a linear code, and if you're transmitting over a binary let's say, symmetric channel, that it doesn't matter actually what the code word was that transmitted. The only thing that matters is what the noise is. In this case, what's the erasure pattern. Okay, so we can encode whether or not this succeeds or not by simply listing where the erasures happen. That's the only thing we need to know. And so this is exactly what this set omega I will be. It's of length of only n minus 1 because the observation itself doesn't matter. And we'll simply store in there, in this set, all the vectors that give us trouble. Now, if you think a little bit about what vector will give you trouble, well, you might imagine that the all zero code word was transmitted. So what you're going to look for is all the code words that are compatible with the observed value y. The all zero is compatible. So the only question now is if we want to decode the ith bit, if there's a code word that's compatible that has a 1 in the ith position. Because if there's a code word that has a 1 in the ith position, we also know that there's a code word that has the 0 in the ith position. By linearity, there must be the same number of code words that have a 0s and 1s in the ith position, and then we don't know if it was a 0 and 1. Okay, so is there a code word that in the ith position has a 1? So does there exist a code word such that the ith position is 1 and it is covered? It is covered by this noise. Okay, so this is the code word presumably here. It has a 1 in here. This is the noise. So wherever there's a 1, there's an erasure. And why do we worry about covering? Because if there's an erasure, we don't actually see what's happening. And so this code word looks to us exactly the same as the all zero code word. And so we will not be able to distinguish if it was the all zero or this particular code word. Okay, so these are the vectors that should be in there. Okay, and now what is then the probability of error for such a decoder? Well, it's exactly this measure, this Bernoulli measure of the sets. It's exactly the probability that we get one of these bad erasure patterns, and so this will give us rise to a curve like this. Good, so now what do we want to do? Well, obviously we want to use this sharp thresholding result. So we want to show that it is monotone, we want to show that it's symmetric, and we also want to show that actually all these functions are the same. It doesn't matter which component we're looking at. These are the 3 components, so let me quickly go over them. The first one is pretty obvious, right? What was again the condition? There must exist, I'm looking at the ith component here. I'm looking at the component, I'm looking at the ith position, I'm looking at a code word. This code word must be a 1, and the noise must cover it. Well, what happens if I'm adding some more noise to it? For example, I'm switching this 0 to a 1, okay, so that's what monotonicity means. I'm adding some extra 1s to it. Well, if I'm adding an extra 1, that clearly also covers that, right? So hence, this condition is here, so hence, this vector will also be in the bad set, so clearly this set is monotone, right? So that's pretty clear that if I have a decoder, it can't decode, I'm adding extra noise to it, it's not going to get better by that. Good, so the second one, symmetry, is a little bit more tricky, and so now we have to use the symmetries of the code. So the claim is that if the code is too transitive, then the set will also be symmetric. Right, so let's check a little bit why this is true. So again, we have a position I. This is the noise pattern that I get. That's the code word that gives us trouble because it's covered and has a 1. But now remember that a too transitive code, I can take any pairs of position and map it to any other pairs of position such that the code stays invariant. Right? So let me define now which of these mappings I want. Well, I want a map such that the ith position maps into itself. That's one condition I want, okay? And now I can take any j and map it into any k here, right? So there is then a permutation on this set of indices. The I maps into I, the j maps into k. And I can also, of course, just look at the restriction of this permutation just on the sets on the n minus the I if I'm looking at everything else, right? Now remember, this permutation I can pick in such a way that the code stays invariant. And so what happens now if I do this? Well, I want to prove that now if the omega is in here, right, if this noise is in here, that if I'm now inducing this permutation on this noise here, that the permuted version is also in there. That's what the symmetry means. That's what the one transitivity means for this set. And that's fairly clear, I guess, right? So you have the omega in there. This means there exists this code word that is 1 there and is covered. Now if I apply this permutation to it and define a new code word here, which is the permutation of this code word, well, we picked it such that the ith position goes again to itself. So again, the ci of the hat is again 1. And now all we are doing is we're permuting the code word, right? And we're permuting the noise, but it's permuted together, so nothing really changes. So this proves that now also this permuted noise is actually in there. Okay, it just means we're taking the code word, we permute it a little bit, we're taking the noise that before covered the code word, permuted in the same way. So, the permuted version will now cover the permuted code word, and hence this proves that indeed this is in there. Okay, so it's fairly straightforward, and now here remark that we have used the true transitivity of this code. And the final one is that we want that these exit functions actually do not depend on the position. Why do we want this? Because remember, the area theorem applies to the average, and if all of them are the same, then actually it applies to an individual one, right? If they're all the same, the average is equal to a single one, and then every single curve actually fulfills the area theorem. And so how do we do this? Well, I think that's, without going through it, that's fairly obvious. Again, we're using code symmetry, but now it's only the one transitivity, right? Every single position is the same because it can map any position to any other position. The channel is memoryless, so it doesn't matter, which positions, how I'm permuting the position, the order of position doesn't matter. And hence, every single position behaves the same. They all have exactly the same error probability. Okay, so now we are almost done. Let's just put all these things together. So we have monotonicity, symmetry, and now we can apply this Friedgut-Kalai result, right? So they tell us that this transition for the HI, for the error probability that's associated to this exit decoder, is sharp in the sense that this transition here is of order 1 over log n. And so if I'm making the n larger and larger, right, what will have to happen is that this transition essentially, or this function becomes a step function, right? Now, but as we mentioned beforehand, that's fine, except where does this transition happen, right? We don't want this transition to happen just anywhere, right? But now we recall that these exit functions here, if I'm averaging them out, that they actually fulfill this area theorem, right? So hence, by the area theorem, the area inside here must be exactly the rate of the code, right? But since this is a step function, where does this position have to happen? Well, exactly at 1 minus the rate of the code, so the epsilon parameter, the critical one where this jumps is exactly 1 minus the rate, but that's exactly capacity, and we're done. Okay? So that's the end of the proof. That's, all the proof. I basically left out nothing of the proof here, and you've seen how these three components come together to show that we achieve capacity. So let me summarize one more time. We have three components that we used, and these are the only ones that we have used. We have used that the code is symmetric, and symmetric in the sense that it is two transitive. We have used the function that symmetric and monotone functions have this sharp threshold result. And one of the favorite things that I like about this is that we've used the exit function. And why do I like it? Because recall that the exit functions were introduced to analyze iterative codes, right? They're stands as much for iterative decoding as you can, versus here we're looking at something that stands for as much classical coding as we can think of, okay? And nevertheless, it's exactly this ingredient that allows you to figure out where the threshold is, okay? And when we put all these three components together, we see indeed that we achieve capacity. Good, so maybe just to wrap up, right now, if you plug this all in and so on, you will see that that the bit error probability is as small as you want to. If you want to get block, one way to do it is to use a slightly sharper version of this thresholding result that allows you to show that this error probability that you can pick, remember it was sharp, but from where to where, okay, that the width is still very small if we're asking that to be going down faster than 1 over n, and then we can just use the union bound to get the block error probability, okay, so that takes care of this. Other codes, well, the only thing we have used is this two transitivity. There are other classes of codes in principle that you can apply this to. And finally, of course, the big question is what happens to gen on channels. Would be nice if to say, oh, trivial, can do it, okay. We are, cautiously optimistic. All the ingredients that you need in principle there for the general case. Symmetry has nothing to do with the channel. Exit functions, we have generalized exit functions, fulfill the same thing. It's just technically more difficult. Not saying it's trivial, but I think in principle, if you have the right tools and and enough tenacity, I think one should be able to extend this result. Now, if we get back, okay, to to the Simons Institute, which we also thank for hosting us, was great. We'll be happy that we can put one check mark, at least for the BSc, okay, not a complete check mark. And that finished my talk, and thank you very much.
So thank you very much, Ruediger, Henry, and Aaron, and Marco, and for a wonderful talk. And it was wonderful both for the result and for the presentation. So any questions? So,
Rudi, there is a result by Peleg and myself and Sandarovich on extrinsic information of good codes on Gaussian chance using IMMC things, which you have the same threshold of the RFN.
Right, you have a result that for some codes you have, I can't remember exactly what the condition
Any
was.
good codes that can approach capacity should behave the very same way. In terms
Any
of
good code behaves
the very same way. Any.
So it's not true in general, right? These are non-trivial conditions. For example, if you think of LDPC codes, right, they do not achieve capacity, but have almost all the properties that you want in the ingredient of the proof, right?
We have examples also there in the work with Calderman here on the LDPC codes.
Right, but what is your statement exactly?
Any good code that achieves capacity, exactly as we know the MMSC.
Sure, any good, but that's the definition of a good code, right? A good code means that it achieves capacity, means it has to jump, right? So
No, but you know the MMSC behavior and you know the exit charge behavior.
sure, but essentially that's by definition, right?
It's not that's it.
Yes.
So
I agree.
it appears that.
The question was, can you take it anything about the decoding time complexity and so on? So this is purely achieving capacity, and maybe we should have said this still. This is the very first step of, just to saying this should be interesting. And now, in order to make this useful, or in saying that this is useful, we would have to find an algorithm that somehow uses something like polar codes to bring this down to a reasonable complexity. Right now, there's no decoder associated that would get you that result.
Yeah, probably the biggest open practical question is there a low complexity decoder for Reed-Muller codes? And that's something I think the TCS community excels at, finding approximations or something like this. So we'd be very happy if somebody found one.
any other questions?
This is all for binary, right? I mean, if you're just exploiting these algebraic properties, could there be potential for like higher query alphabet codes?
Can you just repeat?
Oh, I'm saying, so this is all for binary. I'm saying if you had higher order alphabets.
Right, okay, so Reed-Muller codes also exist in higher order alphabet. We have not looked at that, okay? I don't know if one could do a similar type of proof. In principle, the concepts are there, but again, it might be much more complicated.
So to expound on that, actually, you can extend it to pretty much any QRA channel. So essentially, with small changes in the definitions, everything goes through for QRA erasure channels. Getting away from erasure could be much harder. But, so.
Other questions? Can you use the mic?
So what does the current analysis give you in terms of probability of error? Is it something like 1 over polylog or
yeah, in this other result, it goes down like the window like log squared of 1 over, you have log squared of 1 over epsilon. So you can do any, I guess you could do any power of n or something like that. I have to think about what that means. Okay.
Yeah, I think you can get is faster than any polynomial in n. If you use the extended framework, the Bourgain-Collai.
Good.
So let's take the BEC. So the proof that polar codes achieve capacity is very different than what you presented. But I wonder if there's a connection, and let me explain why. Okay, so here you have the sharp threshold, this sort of phase transition in the exit function. In polar codes, you can think of the polarization effect as also a sharp threshold. So do you think there's a connection? I mean, it's in different things, but I'm wondering if there's a connection.
So, that you have a sharp threshold is, according to Tillich and Seymour already, that, that's true for almost all these codes have minimum distance, square root of block length, and you can pretty much anything from this matrix. So all of them would have a sharp threshold. The fact whether or not it's at capacity or not, that needs something extra. Okay, for polar, that's given, when you analyze the polar transform, and here it's some slightly different thing. But there, you always need to seem to use something very specific.
Other questions?
So can you tell us, I mean, you told us why, you told us it didn't work for the binary symmetric channel, but can you just sort of elaborate on it? It seemed like all the three ingredients were working and yet something doesn't.
Well, we're not saying it's not working, but this is fairly fresh, okay? And it's literally just the last month, and so for general channels, you no longer have just a 0-1 function, right? So in general, the probability of error, there will be some probability of error that you have. So it's a function that takes values, let's say, between 0 and 1. And so there don't seem to be in the literature just things you can just plug and play. I think you need to be able to go down to the actual level and unravel everything, and that takes much more time. This, the one result we used is quite fundamental and is not just something trivial that you can extend.
We have time for some more questions if there are any. Yeah. Yeah.
So intuitively, the Reed-Muller code, should be achieving capacity because it has better minimum distance behavior than polar codes. And so is there any general recipe of connecting the minimum distance to actual, threshold you achieve if there is enough symmetry in the code?
So that's a good question, and it's not clear. The proof we have uses only the symmetry, and for the block map, you need only the minimum distance. And it's not clear mixing these helps or gives you more or less. I know that Rudy and his students worked for some time trying to write a proof of this using polar codes, and so I think that path must be harder, I will say.
Yeah, it's not obvious how to do it, but there might be some general statements of this kind there, but we don't know.
Other questions? All right, if not, we want to thank Ruediger and Henry and all the co-authors for an absolutely fantastic presentation.
All right.
And also making it an extremely exciting plenary talk, and perhaps among the shortest ones in many ways, with a great result. So thank you very much again.